There's a storm in space that's been raging for 340 years. A hurricane 3 times wider than Earth that should have died centuries ago. And we still don't know why it exists. But that's just the beginning. What you're about to discover will change how you see the night sky forever. We think of space as peaceful, silent, a canvas of twinkling stars where nothing ever changes. We're wrong. The universe is violent, it's chaotic, and there are places out there so extreme, so fundamentally hostile to existence itself, that calling them terrifying almost feels inadequate. Places where planets rain molten glass sideways at 7,000 kilometers per hour, where stars cannibalize each other in gravitational death spirals, where entire solar systems are ripped apart by invisible cosmic monsters we're only beginning to understand. Today, we're going on a journey to these places. Not the ones you've heard about in school, not black holes or supernovas. Those are just the opening act. We're going deeper, to the places astronomers whisper about. The cosmic nightmares that make even seasoned scientists pause and wonder if we're truly ready to explore what's out there. From rogue planets drifting through eternal darkness, to stars that pulse with the energy of atomic bombs every single second. From worlds where the sky itself is poison, to regions where reality literally tears apart at the seams. This is the universe unfiltered, the cosmos without mercy. Let's begin with something that shouldn't exist at all. Picture a hurricane, not the kind that batters coastlines and disappears after a week, but one that never stops, never weakens, never dies. Jupiter's Great Red Spot is exactly that. A storm so massive you could fit 2 or 3 Earths inside it, and it's been churning in Jupiter's atmosphere since at least 1665. That's over 3 centuries. Think about that. When humans first observed this storm through telescopes, the Renaissance was still happening. The United States didn't exist. The Industrial Revolution hadn't begun. And this storm? It was already ancient then. But here's what makes it truly terrifying. We don't fully understand why it won't die. On Earth, hurricanes need warm ocean water to survive. Cut off that energy source, and they fade within days. Jupiter has no surface, no oceans, no ground. It's a gas giant, a planet made almost entirely of hydrogen and helium, with a small rocky core buried impossibly deep below layers of liquid metallic hydrogen. So what's feeding the Great Red Spot? Inside this storm, winds reach speeds of 680 kilometers per hour. The temperature at its core is hundreds of degrees hotter than the surrounding atmosphere. Lightning bolts crackle through clouds of ammonia and methane, each strike powerful enough to vaporize a building. And it's shrinking. When astronomers first measured it in the 1800s, the Great Red Spot was more than 40,000 kilometers wide. Today, it's less than half that size. It's been steadily contracting for over a century, growing taller and more intense as it condenses, like a dying star collapsing into something denser and more powerful. Scientists don't know if it will vanish completely, stabilize, or potentially spawn new storms as it breaks apart. What they do know is that whatever happens will be unlike anything we've seen before. But the Great Red Spot isn't alone. Jupiter's atmosphere is a battleground of competing storm systems. There's the Little Red Spot, a younger sibling born from the merger of 3 smaller storms in 2000. There are white ovals, brown barges, and countless smaller vortices, all swirling and colliding in a dance of chaos. Imagine standing on the cloud tops if you could. The sky above you would be a kaleidoscope of swirling colors, reds, browns, whites, oranges, each band representing different chemical compositions and temperatures.
the horizon would curve dramatically, revealing a planet so massive that its gravity alone creates atmospheric layers stacked kilometers deep. And below? Below is something far more terrifying. Beneath those beautiful clouds lies a layer of liquid hydrogen, compressed by pressure so extreme it behaves like molten metal. Deeper still, temperatures reach 20,000 degrees Celsius, hotter than the surface of the sun. At Jupiter's core, crushed under the weight of an entire planet, conditions are so violent that atoms themselves are torn apart. The Great Red Spot is just the surface manifestation of Jupiter's true nature, a planet-sized engine of perpetual chaos, powered by internal heat that's been radiating since its formation 4.6 billion years ago. It's a reminder that the universe doesn't play by our rules. On Jupiter, storms don't need oceans, they don't need land. They just need energy. And Jupiter has energy to spare. 340 years. Longer than nations, longer than empires. And still, it rages on. 50 light years from Earth, there's a planet that looks deceptively beautiful. From a distance, you'd see a stunning cobalt blue sphere, almost like a twin of Earth hanging in the darkness of space. But get closer, and you'd realize you're looking at hell. This is HD 189333b, and it's one of the most hostile worlds ever discovered. The blue color isn't from oceans or a friendly atmosphere. It's from silicate particles in the air, tiny fragments of glass suspended in clouds that circle the planet at over 7,000 kilometers per hour. That's nearly 7 times the speed of sound on Earth. Imagine that. Glass shards, razor thin and superheated, whipping through the atmosphere sideways at speeds that would shred anything in their path. But it gets worse. HD 189333b is what astronomers call a hot Jupiter. It's a gas giant, similar in size to Jupiter, but it orbits its star at a distance closer than Mercury is to our Sun. It completes one full orbit in just 2.2 Earth days. Because of this extreme proximity, one side of the planet is permanently facing its star, locked in eternal daylight. The other side faces away, trapped in eternal night. And the temperature difference between these two hemispheres drives winds of unimaginable ferocity. On the day side, temperatures soar to 1,200 degrees Celsius, hot enough to melt aluminum. The atmosphere becomes a furnace of vaporized metals and silicon compounds. These particles condense into clouds on the cooler night side, forming droplets of molten glass. Then the winds take over. Atmospheric circulation drags these glass clouds across the planet at hypersonic speeds, creating storms that dwarf anything Jupiter has ever produced. And as the glass droplets cool, they harden into crystalline shards that rain down sideways, driven by winds that never stop. If you could somehow survive on this planet's surface, which you couldn't, because there is no surface, only layers of increasingly dense gas, you'd experience conditions beyond any earthly nightmare. The sky would glow a deep azure blue, beautiful and utterly lethal. The air itself would be a weapon, each breath filled with microscopic glass particles that would shred your lungs. The heat would vaporize you in seconds, and if by some miracle you remained intact, the wind would flay you alive with billions of tiny blades moving faster than bullets. But HD 189733b reveals something profound about the universe. Beauty and horror aren't opposites. They're often the same thing, viewed from different angles. This planet is stunning. Photographs from the Hubble Space Telescope show its blue hue clearly, a jewel among the stars. But that beauty is a lie, or at least a trick of light and chemistry. The same silicate particles that make it blue also make it deadly. And HD 189733b isn't unique. Astronomers have discovered hundreds of hot Jupiters throughout our galaxy. Many likely have similar conditions: extreme temperatures, supersonic winds, and atmospheres filled with exotic compounds that would be toxic or corrosive to anything we know. Some rain iron. Others have clouds of rubies and sapphires forming in their upper atmospheres before being torn apart by turbulence. There are worlds where the sky literally glows red from sodium vapor, and planets where it snows sunscreen, titanium oxide condensing into white flakes that drift through alien clouds. The universe is more creative with horror than we ever imagined. HD 189733b also taught us something else. These extreme worlds are common. For every Earth-like planet we hope to find, there are dozens of cosmic hellscapes, each more inhospitable than the last. And somewhere out there, perhaps in a solar system we haven't discovered yet, there might be a planet even worse. A world where the rain isn't glass, but something even more exotic. A world where the atmosphere itself is a chemical weapon. A world where simply existing on the surface would be an impossibility. But we'll never know unless we keep looking. And that's both the promise and the terror of space exploration. Every new discovery reveals just how much stranger, how much more dangerous, and how much more beautiful the universe truly is. In 1967, a graduate student named Jocelyn Bell Burnell was scanning radio telescope data when she noticed something impossible. A signal, repeating, precise, once every 1.337 seconds, like clockwork. At first, astronomers thought it might be aliens. They even nicknamed the signal LGM1, Little Green Men. It wasn't aliens. It was something far stranger. What Bell Burnell had discovered was a pulsar, a neutron star spinning hundreds of times per second, beaming radiation into space like a cosmic lighthouse. But to understand how terrifying pulsars truly are, we need to understand how they're born. When a massive star exhausts its nuclear fuel, its core collapses in a fraction of a second. The outer layers rebound in a supernova explosion so bright it can briefly outshine an entire galaxy. And at the center, crushed under gravity beyond comprehension, the core becomes something that shouldn't exist: a neutron star. Take all the mass of our sun and compress it into a sphere just 20 kilometers across. That's roughly the size of a city. But in that tiny space, matter is packed so densely that a single teaspoon would weigh as much as a mountain, about 1 billion tons. At this density, atoms themselves collapse. Electrons and protons merge into neutrons, and the entire star becomes a single atomic nucleus, held together not by molecular bonds, but by the sheer pressure of its own gravity.
But neutron stars don't just sit quietly in space. They spin rapidly. When the core of a star collapses, it retains its angular momentum. But as the radius shrinks, the rotation speeds up dramatically, like an ice skater pulling their arms in during the spin. Some pulsars rotate over 700 times per second. That's not a typo. 700 rotations every single second. At that speed, the surface of the star is moving at a significant fraction of the speed of light.
The forces involved are so extreme that if the star were even slightly less dense, it would tear itself apart. And here's where it gets truly disturbing. As these neutron stars spin, they emit beams of radiation from their magnetic poles. If those beams happen to point toward Earth, we detect a pulse each time the star rotates, hence the name pulsar. But these aren't gentle radio waves. Pulsars emit across the electromagnetic spectrum: radio waves, visible light, X-rays, and gamma rays. The energy output is staggering, powered by the star's rotation and its magnetic field, which can be trillions of times stronger than Earth's. Some pulsars are so energetic they create pulsar wind nebulae, regions where particles accelerated to nearly light speed collide with surrounding gas, creating ghostly clouds that glow with high energy radiation. And then there are millisecond pulsars. These are neutron stars that spin even faster, hundreds of times per second, their surfaces experiencing forces that would liquefy any normal matter. They're often found in binary systems, stealing matter from a companion star and using that material to spin up even faster. Imagine being near one. The magnetic field alone would be lethal. Any electronics would fail instantly. The radiation would fry you in seconds. And if you somehow got close enough to see the surface, you'd witness something from a nightmare. A sphere rotating so fast it blurs, its poles shooting jets of particles into space at relativistic speeds, the entire object pulsing with energy like a mechanical heart. But the most terrifying pulsars aren't the ones we can see. There are rogue neutron stars out there, speeding through the galaxy at hundreds of kilometers per second, remnants of supernova explosions that gave them a gravitational kick. These objects are small, dark, and incredibly difficult to detect unless they happen to emit radiation in our direction. And if one were heading toward our solar system, well, let's just say it wouldn't be good. Pulsars are a reminder that even in death, stars refuse to go quietly. They collapse, condense, and transform into objects so extreme that our understanding of physics is barely enough to describe them. They're cosmic sirens screaming into the void at frequencies we can detect but barely comprehend. And somewhere out there, in the cold darkness between stars, one might be heading our way, spinning, pulsing, waiting.
Not every planet orbits a star. In the darkness between solar systems, there are worlds drifting alone, untethered, homeless, cast out from their birth systems or formed in isolation. These rogue planets wander through interstellar space with no sun to warm them, no star to light their skies. And there are billions of them. Astronomers estimate that rogue planets might outnumber stars in our galaxy. For every sun-like star, there could be dozens of these orphaned worlds tumbling through the void, invisible except for the rare occasions when they pass in front of a distant star or emit faint infrared heat. But what would it be like on one of these worlds? Imagine a planet frozen in time. No day, no night. Just eternal twilight, if you could even call it that. The sky would be black, not the blue or orange we're used to, but a pure, absolute darkness punctuated only by the faint pinpricks of distant stars. There would be no sunrise to mark the passage of time, no seasons, no weather patterns driven by solar heating, just cold. Relentless, unimaginable cold.
On a rogue planet, surface temperatures would plummet to near absolute zero. Any atmosphere would freeze and fall as snow. Oceans, if they ever existed, would be locked in ice kilometers thick. Even the ground itself would be frozen solid, its rocks and minerals held in stasis by temperatures that would make Antarctica look tropical. But here's the truly unsettling part. Some of these rogue planets might still harbor life. Deep beneath their frozen surfaces, heat from radioactive decay in their cores could melt pockets of liquid water. Hydrothermal vents, similar to those found in Earth's oceans, might provide energy for microbial ecosystems to survive. Life without sunlight. Life without stars. Life persisting in absolute isolation, unaware that it's hurtling through the galaxy at hundreds of kilometers per second. Cut off from everything, existing in a bubble of warmth, surrounded by infinite cold. If such life exists, it would never know what stars are. It would never see the cosmos. It would evolve, reproduce, and die in darkness, generation after generation, while its world drifted through the void. And we'd never know it was there, unless we happened to stumble upon it. But rogue planets represent something more than just lonely worlds. They're evidence of cosmic violence. Most rogue planets weren't born alone. They were ejected from their home systems, flung into space by gravitational interactions with larger planets or by the chaotic dynamics of young stellar systems still settling into stability. Imagine being a planet in a developing solar system. Other massive worlds orbit nearby, their gravitational pulls tugging at you, disrupting your path. One day, a close encounter with a Jupiter-sized giant sends you careening outward. Past the orbit of your star, past the edge of the system, into interstellar space. Your sun shrinks to a point of light. Then to just another star among billions. And then you're alone. Your surface freezes, your atmosphere collapses, any life that existed on you dies in the darkness unless it can adapt fast enough to survive on internal heat alone. And you drift for millions of years, perhaps billions. Through the galaxy, past other stars, other systems, always alone. Some rogue planets might pass through other solar systems, briefly warming as they skim past alien suns before being flung back into the void. Others might be captured, becoming new members of stellar systems that aren't their own. But most will wander forever. There's something profoundly melancholy about rogue planets. They're survivors of cosmic disasters, refugees from stellar chaos. They're proof that the universe can be cruel, that not every world gets a happy ending. And here's the most disturbing thought. Earth could become one. It's unlikely, but not impossible. If a rogue star passed through our solar system, or if a nearby supernova sent a neutron star racing in our direction, the gravitational disruption could eject Earth from orbit.
We'd drift away from the sun, watching it shrink in the sky as temperatures plummeted. Within weeks, the surface would freeze. Within months, the atmosphere would begin to snow out. Within a year, Earth would be a frozen shell, lifeless except perhaps for microbes deep underground near geothermal heat sources. And humanity? We'd have to adapt or die. Maybe we'd build underground cities heated by nuclear reactors. Maybe we'd migrate to space stations. Or maybe we'd simply vanish, another failed experiment in a galaxy that doesn't care. Rogue planets are the universe's way of reminding us that nothing is permanent. Not orbits, not solar systems, not even the stars themselves. Somewhere out there, in the darkness between stars, a rogue planet is drifting past. Its surface is frozen, its skies are black, and no one will ever know it existed unless we happen to detect the brief gravitational lensing event as it passes in front of a distant star. It's a ghost world, a cosmic wanderer, a planet without a home. And it's not alone. There are billions more drifting silently through the galaxy, waiting to be discovered. Or perhaps, waiting to discover us. In binary star systems across the galaxy, something horrific is happening. One star is slowly devouring its companion, siphoning away matter in a gravitational feeding frenzy that can last millions of years. These are vampire stars, and they're far more common than you'd think. Most stars aren't alone. About half of all stars in our galaxy exist in binary or multiple star systems, orbiting each other in a cosmic dance. And when these stars age at different rates, things get dark. Imagine two stars, born together from the same cloud of gas. The larger one burns brighter and faster, exhausting its fuel first. It swells into a red giant, its outer layers expanding until they reach toward its companion. That's when the feeding begins. The smaller star, still in its prime, begins pulling material from the bloated outer layers of its dying partner. Gas streams between them in glowing arcs, spiraling down onto the vampire star in an accretion disk that heats to millions of degrees. From a distance, you'd see a pair of stars connected by a bridge of light stellar matter flowing like blood through space, transferring from one star to another. But this isn't a gentle process. As the vampire star gorges itself, it grows hotter, brighter, and more unstable. If it's a white dwarf, the dense remnant of a sun-like star, it has a limit to how much mass it can hold. Add too much, and it can't support its own weight. That's when it explodes. Type 1a supernovae, some of the most powerful stellar explosions in the universe, are created when white dwarf vampire stars consume too much matter. They reach a critical mass, about 1.4 times the mass of our Sun, and collapse catastrophically, triggering a thermonuclear detonation that tears the entire star apart. In a fraction of a second, the white dwarf is completely destroyed. The energy released is so immense that it briefly outshines every other star in its galaxy combined. And the blast wave? It expands outward at 10,000 kilometers per second, vaporizing anything in its path. If Earth were orbiting a white dwarf vampire star, we'd never see it coming. One moment, two stars would be orbiting peacefully. The next, a flash of light would erase our entire solar system before the radiation even reached us. But not all vampire stars explode. Some feed more carefully. There's a type called blue stragglers. These are stars in dense star clusters that appear younger and bluer than they should be. They've stolen so much matter from companions that they've effectively reversed their aging process, gaining mass and extending their lifespans while their victims shrink and fade. It's cosmic parasitism on a stellar scale.
Then there are the most extreme cases, neutron star vampires. When a neutron star has a binary companion, its gravitational pull is so intense that it rips material away at relativistic speeds. The stolen matter forms an accretion disk, spiraling into the neutron star, heating to tens of millions of degrees and emitting X-rays so powerful they can be detected across the galaxy. These systems are called X-ray binaries, and they're some of the brightest X-ray sources in the night sky. The neutron star spins rapidly, often hundreds of times per second, and the infalling matter releases more energy than 1,000,000 suns. But here's where it gets truly disturbing. The companion star is being killed slowly. Over millions of years, the neutron star will consume its partner completely. First, the outer layers are stripped away. Then the core begins to erode. Eventually, nothing will remain except the neutron star itself, bloated with stolen mass, spinning alone in the darkness. It's not a quick death. It's gradual, inevitable, a cosmic horror story playing out in slow motion across the galaxy. And sometimes, the vampire doesn't stop. If a neutron star accumulates enough mass, either from a companion or from multiple feedings, it can collapse further, crossing the threshold into something even more terrifying: a black hole. When that happens, the feeding doesn't stop. It intensifies. The black hole's appetite is infinite, limited only by how much matter it can pull from nearby space. And if there's a companion star still orbiting, it becomes trapped in an inescapable death spiral. Scientists call this the Roche limit, the point where tidal forces from the black hole overcome the star's own gravity. Once crossed, the star is torn apart, stretched into a stream of plasma that spirals into the black hole's event horizon. From a distance, it looks almost peaceful, a glowing disk of light surrounding darkness. But up close, it's violence beyond comprehension. Temperatures reach billions of degrees, magnetic fields twist and snap, and jets of particles shoot outward at near light speed, piercing through space for thousands of light years. The star is being murdered, slowly, publicly, and there's nothing it can do to escape. Vampire stars remind us that even in the cosmos, survival often means sacrifice, that beauty and horror coexist in systems where stars feed on each other, where the strong consume the weak, and where death comes not as a single event, but as a long, drawn-out process measured in millions of years. Somewhere in our galaxy, right now, a star is being drained. Its light is fading. Its mass is flowing away, and its companion grows brighter, fed on the corpse of what was once its equal. And we call this evolution. In 2008, astronomers noticed something that shouldn't exist. Galaxy clusters, thousands of them, were moving in the same direction, as if being pulled by something beyond the edge of the observable universe. This phenomenon is called dark flow, and it challenges everything we thought we knew about cosmology. Let me explain why this is so disturbing. According to our current understanding, the universe expanded from the Big Bang in all directions. As it did, matter distributed itself relatively evenly, forming galaxies and clusters that on the largest scales should move randomly based on local gravitational interactions. But they don't. All of them moving together, as if something enormous, something beyond our cosmic horizon, was pulling them. The speed is significant too, about 1,000 kilometers per second. That's fast enough to be measurable, undeniable, and deeply unsettling. Because if there's something out there with enough gravitational influence to drag galaxy clusters across hundreds of millions of light years, it would have to be unimaginably massive, larger than anything in our observable universe. Some theories suggest it could be a megastructure of dark matter. Others propose it might be gravitational influence from another universe entirely, a neighboring cosmos pressing against ours like a bubble touching another bubble in a cosmic foam. But here's the truly terrifying part. We may never know what's causing it. The dark flow points toward a region beyond our observable universe, beyond the cosmic horizon, where light from those distant places hasn't had time to reach us yet.
In fact, due to the expansion of space itself, light from whatever is pulling us will never reach us. It's like being pulled towards something in the dark. You can feel the motion, you can measure the direction, but you'll never see what's pulling you. And as the universe continues to expand, that pull might grow stronger, or it might fade, or it might remain constant, forever tugging at the fabric of space-time while we drift helplessly toward an unseen destination. Some scientists are skeptical. They argue that dark flow could be a statistical anomaly, a misinterpretation of data, or the result of calibration errors in our instruments. After all, measuring the movement of galaxy clusters across such vast distances is incredibly difficult. But other researchers have confirmed the findings using independent methods. The clusters are moving, all of them, in the same direction. And that raises a haunting question. What else is out there that we can't see? If dark flow is real, it suggests that the observable universe, everything we can detect, measure, and study, is just a tiny fraction of reality. Beyond our cosmic horizon, there could be structures, forces, and entities so vast that they dwarf everything we know. Imagine standing in a dark room, feeling a breeze. You know something is there. A window, a fan, something moving air. But you can't see it, you can't touch it. You can only feel its effect. That's where we are with dark flow. We're feeling something pulling us, something massive, something beyond reach, and we have no idea what it is. There's also the possibility that dark flow is evidence of a multiverse, that our universe isn't alone, that beyond the edge of what we can observe, other universes exist, each with their own physics, their own galaxies, their own rules. And perhaps one of those universes is close enough that its gravity bleeds through, tugging at our galaxy clusters, pulling them toward a boundary we'll never cross. If that's true, then we're not just in a universe, we're in an ocean of universes, each influencing the others in ways we're only beginning to detect. But even that explanation doesn't answer the deeper question, why? Why would galaxy clusters feel this pull, but not individual galaxies? Why does the effect diminish over certain distances? Why does it point toward one specific region of space? The more we study dark flow, the more questions emerge. And the answers, if they exist, lie forever beyond our reach. It's a humbling reminder that for all our telescopes, all our mathematics, all our theories about how the cosmos works, we're still standing on a very small island in an ocean we don't understand. And somewhere in the darkness, something is pulling us. We don't know what. We don't know why. Only we know we are moving, and we can't stop. Imagine the universe as a spider's web. Galaxies aren't scattered randomly. They're connected by invisible threads, forming a vast cosmic network that spans the entire observable universe. This is the cosmic web, and at its intersections, something invisible is waiting. Dark matter. We can't see it, we can't touch it, it doesn't interact with light or any form of electromagnetic radiation, but we know it's there because we can see its gravitational effects on everything around it. Dark matter makes up about 85% of all matter in the universe. Let that sink in. Everything we can see, stars, planets, nebulae, galaxies, is only 15% of what's actually out there. The rest is dark, hidden, lurking in halos around galaxies, threading through the cosmic web like a skeleton, holding everything together. But here's where it gets disturbing. Dark matter isn't evenly distributed. It clumps together in massive halos, invisible structures that surround galaxies and galaxy clusters, shaping how they move and interact. Our Milky Way is embedded in one of these halos, Right now, as you read this, dark matter is passing through your body. Billions of particles every second, streaming through the Earth, through the atmosphere, through you, without a trace. You can't feel it, you can't detect it directly, but it's there. And we have no idea what it actually is. There are theories, of course. Some scientists think dark matter is made of weakly interacting massive particles, WIMPs, hypothetical particles that barely touch normal matter. Others propose axions, primordial black holes, or even more exotic candidates. But despite decades of searching, we haven't found a single dark matter particle, not one. Labs around the world are filled with detectors designed to catch the faintest whisper of a dark matter interaction. They're buried deep underground to shield them from cosmic rays. They're cooled to near absolute zero to eliminate noise. And they wait. But so far, nothing. It's like hunting a ghost that you know exists because it keeps moving furniture, but you can never see it or hear it. You only see what it affects. And the effects are everywhere. Galaxies rotate faster than they should based on the mass of their visible matter. Without dark matter holding them together gravitationally, they'd fly apart. Galaxy clusters are too massive to be explained by stars and gas alone. Even the large-scale structure of the universe, the cosmic web itself, formed because dark matter provided the gravitational scaffolding for normal matter to follow. Dark matter built the universe, and we don't know what it is. But what makes dark matter truly terrifying isn't just its invisibility, it's what might happen if it's not stable. Most dark matter theories assume these particles are eternal, unchanging. But what if they're not? What if dark matter can decay or interact in ways we haven't detected yet? Some scientists have proposed that dark matter could annihilate itself, releasing energy when particles collide. If that's happening in the Milky Way's dark matter halo, we might see faint gamma-ray signals from the galactic center. And we do. There's an unexplained gamma-ray excess coming from the core of our galaxy. It could be dark matter annihilation, or it could be something else. Pulsars, cosmic rays, or other astrophysical sources we don't fully understand. But if it is dark matter destroying itself, then the invisible foundation of our galaxy is slowly evaporating, and we wouldn't notice until the gravitational effects became measurable, by which time it might be too late. There's also the possibility of dark stars. If dark matter can clump densely enough, it might form structures held together by its own gravity. These dark stars would be invisible, emitting no light, but they'd have mass, potentially enormous mass. Imagine a star-sized object made entirely of dark matter drifting through the galaxy. You'd never see it coming. It wouldn't shine, it wouldn't emit radiation, but its gravitational pull would affect anything nearby. If one passed through our solar system, the orbits of planets could be disrupted, asteroids could be flung toward Earth, and we'd never know what caused it until we traced the gravitational anomalies back to their source. Dark matter is the universe's ultimate mystery. It's everywhere and nowhere. It shapes galaxies but refuses to reveal itself. It's the scaffolding of reality, and we're living inside a structure we can't see. And here's the most unsettling thought. What if dark matter isn't passive? What if it's not just invisible matter sitting quietly in halos? What if it's active, dynamic, capable of forming structures we haven't imagined yet? There could be dark matter planets, dark matter asteroids, even dark matter life. Entire ecosystems existing in parallel to ours, invisible and unreachable, occupying the same space, but never touching. We'd never know.
Because dark matter doesn't care about us. It doesn't interact with light or chemistry or biology.
It exists in its own realm, governed by rules we're only beginning to glimpse. And as we drift through the Milky Way's dark matter halo, surrounded by invisible mass that outweighs everything we can see, we're left with a humbling truth. Most of the universe is hidden from us forever. In 1950, physicist Enrico Fermi asked a simple question that still haunts us today. Where is everybody? The universe is 13.8 billion years old. Our galaxy alone has hundreds of billions of stars, many with planets that could support life. Even if intelligent life is rare, the sheer number of possibilities suggests we should see evidence of alien civilizations everywhere. But we don't. The skies are silent. No radio signals, no megastructures, no signs of interstellar empires. This is the Fermi paradox, and one of its most terrifying explanations is called the Great Filter. The idea is simple, but chilling. Somewhere between the origin of life and becoming a galaxy-spanning civilization, there's a barrier, a filter. Something that stops almost every species from advancing. And the horrifying question is, where is that filter? Has humanity already passed it, or is it still ahead of us? Let's explore both possibilities. If the filter is behind us, then we're extraordinarily lucky. Perhaps life itself is incredibly rare. Maybe the jump from simple cells to complex organisms is statistically improbable. Or maybe intelligence is a fluke, a cosmic accident that happens once in a trillion worlds. If that's true, then we might be alone in the galaxy. Not because other life doesn't exist, but because it never gets far enough to build civilizations. And while that's lonely, it's not terrifying. But if the filter is ahead of us, then something destroys civilizations before they can spread to the stars. Something inevitable. Something we haven't encountered yet. And statistically, we're about to hit it. There are plenty of candidates for what this filter might be. Nuclear war? We've already come close. During the Cold War, humanity nearly destroyed itself multiple times. One miscalculation, one faulty radar signal, and civilization ends. Maybe every intelligent species invents weapons capable of self-annihilation and then uses them. Climate collapse. Advanced civilizations need energy. Energy production creates waste. If every species industrializes before developing sustainable technology, they might cook their own planets. We're already seeing this on Earth. Maybe we're not the first. Artificial intelligence. As we approach the creation of superintelligent AI, we're entering unknown territory. If an AI becomes smarter than humans, and its goals aren't perfectly aligned with ours, it could optimize for something we never intended. Paperclips, efficiency, its own survival, and humanity becomes an obstacle to remove. Biotechnology. Genetic engineering and synthetic biology give us the power to reshape life itself. But they also make it easier to create pandemics, either accidentally or intentionally. One engineered virus, one lab accident, and billions could die.
Resource depletion. Civilizations grow by consuming resources, but resources are finite. Maybe every advanced species hits a point where they've used up everything available, and collapse is inevitable. We're strip mining Earth for rare materials already. What happens when they run out? unknown physics. There could be technologies we haven't discovered yet that are inherently dangerous, experiments that destabilize space-time, reactors that create runaway chain reactions, wormholes that collapse into black holes. Maybe every civilization that tries to push beyond certain limits accidentally destroys itself. Or, and this is the darkest possibility, maybe there's something out there, something that hunts. What if the reason we don't see alien civilizations isn't because they're rare, but because something eliminates them before they become detectable? A predator species, a self-replicating AI from an ancient civilization, or something even stranger, a cosmic phenomenon we don't understand yet that specifically targets technological life. If that's the case, then our broadcasts into space, our signals announcing we are here, might be the worst mistake humanity has ever made, because we'd be ringing the dinner bell. The Great Filter doesn't just explain the Fermi paradox, it's a warning. Every day we survive as a technological civilization, we're beating the odds. Every year we don't nuke ourselves, engineer a pandemic, or create a rogue AI is a small miracle. And if the filter is ahead, we won't see it coming. It'll look like progress, like innovation, like the next logical step, right up until it kills us. That's why discovering alien life, especially intelligent life, might be the worst news humanity could receive. Because it would mean the filter isn't behind us, it's ahead. And whatever stopped them is waiting for us too. The universe isn't empty because life is rare. It's empty because something keeps it that way. And we're next.
In the early universe, when the first stars were forming, something impossible happened. Stars so massive they shouldn't exist began to form, and inside them, black holes were born. These were quasi-stars, and they were the monsters of the ancient cosmos. Imagine a star with a black hole at its core, not orbiting near it, not consuming it, but living inside it, feeding on the star's own material from within. Quasi-stars could have been up to 10,000 times more massive than our Sun. Their outer layers would have stretched billions of kilometers across, larger than the orbit of Neptune. And at their centers, black holes thousands of solar masses would be actively consuming the star from the inside out. It's stellar cannibalism on a scale that defies imagination. Here's how they might have formed. In the universe's infancy, clouds of primordial hydrogen and helium were far denser than anything we see today. When these clouds collapsed under gravity, they formed protostars, baby stars still gathering mass. But some protostars were so massive that their cores couldn't stabilize. Instead of igniting in normal fusion, they collapsed directly into black holes, while the outer layers continued to fall inward. This created a bizarre hybrid, a black hole surrounded by an enormous envelope of hot gas, still technically a star, but powered not by fusion, but by the gravitational energy of matter spiraling into the central black hole. The radiation from this process was intense, so intense that it would have lit up the early universe like a cosmic lighthouse, potentially visible from across billions of light years. But quasi-stars were unstable, violently unstable. As the black hole consumed matter, it would release enormous amounts of energy. This radiation would push against the star's outer layers, creating turbulence and shock waves. The star would pulse and writhe, caught between the gravity trying to pull it inward and the radiation trying to blow it apart. Eventually, most quasi-stars would destroy themselves. Either the radiation would blow away the outer envelope, leaving behind a massive black hole and nothing else, or the star would collapse entirely, forming an even larger black hole in a catastrophic implosion. But during their brief existence, perhaps only a few million years, quasi-stars would have been the brightest objects in the universe. And they might explain something we've struggled to understand. How did supermassive black holes form so quickly? We found black holes billions of times the mass of the Sun in galaxies less than 1 billion years old. That shouldn't be possible. Black holes grow by consuming matter, and that process takes time. Unless they started big. If quasi-stars existed in the early universe, their central black holes would have a head start. Instead of forming from a single supernova and growing slowly over billions of years, they'd begin with thousands of solar masses already on hand. Feed that black hole with the remnants of the quasi-star, add millions of years of consumption, and you could grow a 1 billion solar mass black hole in a fraction of the time conventional theories predict. Quasi-stars might be the seeds of the monsters we see at the centers of galaxies today. But here's what makes them truly terrifying. They could still exist. Most quasi-stars would have existed in the early universe when conditions were right for their formation. But in rare, dense environments, like the cores of massive star clusters, or regions undergoing galaxy mergers, similar conditions could occur even today. Somewhere in the universe, a quasi-star might be forming right now. A black hole might be burrowing into the heart of a massive star, consuming it from within, while the star's outer layers continue to shine. And we'd never know, unless we happened to point a telescope at exactly the right patch of sky. Quasi-stars represent something profound about the universe. It's capable of creating structures so extreme, so paradoxical, that they sound like science fiction. A star with a black hole heart, a sun that devours itself, a cosmic chimera that shouldn't exist, but did, and might still. And if we ever detect one, it'll change everything we think we know about stellar evolution, black hole formation, and the early universe. Because quasi-stars aren't just stars. They're bridges between the beginning and the end, between light and darkness, between creation and destruction. They're the universe's way of reminding us that it can always find new ways to be impossible.
Time doesn't pass the same way everywhere in the universe. Near massive objects, time slows down. The stronger the gravity, the more time dilates. This isn't speculation. It's confirmed physics. Satellites orbiting Earth have to account for time dilation, or GPS systems would fail within hours. But take this to the extreme. Near a black hole or inside a neutron star's gravitational field, and time doesn't just slow. It nearly stops. And that creates scenarios more horrifying than any nightmare. Imagine 2 astronauts. One stays in orbit around a black hole, far from the event horizon. The other descends closer, hovering just outside the point of no return. For the astronaut near the event horizon, time passes normally. They feel nothing unusual. Their watch ticks at the same rate. Their heartbeat is steady. But when they look up at their companion in orbit, they see something impossible. Their friend is moving in fast forward, aging decades in what feels like minutes. Stars wheel across the sky, the universe beyond accelerates. And when they finally return to orbit, if they can, they find that years have passed, maybe centuries. Everyone they knew is dead. The mission that sent them is ancient history, and they've aged only days. This is the time dilation nightmare. It gets worse. If you fell toward a black hole and someone watched from the safe distance, they'd never see you reach the event horizon. From their perspective, you'd slow down as you approached, your image red-shifting and dimming until you froze at the boundary, suspended there forever. But from your perspective, you'd cross the event horizon in finite time, pulled inexorably toward the singularity, unaware that to the outside universe, you've been frozen in place for eternity. You'd live two different realities simultaneously. To you, you're falling and will soon die. To observers, you're frozen forever at the edge of the black hole, a ghost image that will linger until the black hole evaporates trillions of years from now. Which reality is real? Both. Neither. Time breaks down at these extremes. But time dilation doesn't require black holes. It happens anywhere gravity is strong. Astronauts on the International Space Station age slightly slower than people on Earth, only a few milliseconds over months, but measurable. Clocks at the top of skyscrapers tick faster than clocks at sea level. On neutron stars, time dilation is extreme. A clock on the surface would run about 30% slower than a clock in orbit. Spend a year on a neutron star's surface, and more than a year passes in the outside universe. But the most disturbing time dilation scenarios involve travel. If we ever build spacecraft capable of near light-speed travel, time dilation becomes unavoidable. Accelerate to 99.9% the speed of light, and time slows dramatically for you relative to Earth. You could travel to a star 100 light-years away, spend what feels like a few years aboard the ship, and return home to find that 200 years have passed on Earth. Your children would be dead, your grandchildren too. Civilizations would rise and fall, and you'd be a relic from the past, biologically younger than your own descendants. This is the time dilation trap. You can travel forward in time easily, just go fast or get close to something massive. But you can never go back. The universe you left will be gone, and you'll be stranded in a future you never asked to see. It's a one-way ticket. And it raises a horrifying question. What if advanced alien civilizations have mastered near light-speed travel but refuse to use it? What if they've realized that relativistic travel is a form of exile, that every journey to the stars is an irreversible leap into the future? You might visit 100 worlds, but you'd never return home to the people you knew. Would you take that journey? Or would you stay, content with the time you have, knowing that the stars are reachable, but the price is everything you've ever known? Time dilation isn't just a physics phenomenon, it's a philosophical nightmare. It tells us that time isn't universal, that the past, present, and future aren't the same for everyone, that two people can experience reality at different rates and both are equally valid. And it means that in a universe with time dilation, causality itself becomes murky. Events don't have a single sequence. Depending on your motion and position in a gravitational field, what you perceive as now can be completely different from someone else's now. The universe isn't a stage where events unfold in order. It's a tangled web of different timelines, each one valid from its own perspective, but none of them absolute. We live in a universe where time is flexible, where the past can be stretched, the future compressed, and the present is different for everyone. And once you understand that, you can never see the universe the same way again.
Beyond Neptune, in the frozen outer reaches of our solar system, there's a region filled with ancient ice and rock. Comets, dwarf planets, and remnants from the birth of the solar system drift in slow orbits, barely touched by the sun's warmth. This is the Kuiper Belt, and it has an edge. around 50 astronomical units from the Sun, about 50 times the distance from Earth to the Sun, the population of objects drops suddenly and dramatically. It's called the Kuiper Cliff, and we don't know why it exists. In theory, the Kuiper Belt should gradually fade out, objects becoming sparser as you move farther from the Sun. But instead, it ends abruptly, as if something cleared out everything beyond a certain point. Or as if something is still there, hiding just beyond our detection. One explanation is gravitational resonance. Neptune's gravity creates zones where objects can orbit stably, and zones where they can't. The Kuiper Cliff might be a boundary where Neptune's influence destabilizes orbits, flinging objects either inward or outward over millions of years. But that doesn't explain everything. Another theory is more unsettling. There might be something out there we haven't found yet. A planet, or multiple planets, small enough to evade detection, but large enough to gravitationally shepherd the Kuiper Belt, defining its outer edge. Astronomers call this hypothetical object Planet 9, or Planet X. Not the Planet 9 we've been searching for closer in, but something even farther out, lurking in the darkness beyond the Kuiper Cliff. If it exists, it would be a true ghost world, too faint to see directly, too far to visit, existing in eternal twilight where the Sun is just another star. But here's where it gets strange. Some scientists have noticed that certain distant Kuiper Belt objects have oddly aligned orbits. Their paths seem to cluster, as if being influenced by a massive, unseen body, pulling them into similar trajectories. This could be random chance, or it could be evidence of something massive hiding in the outer solar system, something we've never detected because it's too dark, too distant, or moving too slowly to stand out against background stars. And if there is a planet out there, it raises uncomfortable questions. How did it get there? Was it part of our solar system's original formation, flung outward by gravitational interactions with Jupiter and Saturn? Or is it something else, a rogue planet captured by the Sun's gravity as it drifted through interstellar space? If it's captured, then it's an intruder, a foreign object that wandered into our solar system and decided to stay. And if it's a rogue planet with a stable orbit, it might not be alone. There could be others, hidden in the darkness, too faint for our telescopes to detect. But there's an even darker possibility. What if the Kuiper Cliff isn't a natural boundary at all? What if it's artificial? Some fringe theories suggest that advanced civilizations could use megastructures to mine the outer solar system for resources. If an alien civilization harvested the Kuiper Belt billions of years ago, they might have left behind an artificial edge, a line where they stopped collecting material. It sounds absurd, but the Kuiper Cliff is strange enough that it's worth considering all explanations, no matter how unlikely. The truth is, we don't know what's out there. Beyond Neptune, beyond Pluto, beyond the Kuiper Belt, our solar system fades into darkness. We've only scratched the surface of that region. Only a few spacecraft, Voyager 1, Voyager 2, New Horizons, have ventured that far, and they're tiny probes with limited instruments.
Most of the outer solar system remains unexplored, unmapped, unknown. And every time we look closer, we find something unexpected. Dwarf planets with moons,
objects with strange orbits, mysteries that don't fit our models. The Kuiper Cliff is just one of those mysteries, a boundary that shouldn't exist but does. A line where the solar system seems to say this far and no further. And beyond it, we can only guess. Maybe nothing, maybe more of the same, or maybe something waiting to be discovered, something that will change how we understand not just our solar system, but the universe itself. Because if there's one thing space exploration has taught us, it's that every answer reveals 10 new questions. And the darkness beyond the Kuiper Cliff is full of questions we haven't even thought to ask yet. Galaxies don't live in isolation. They move, they interact, and sometimes they devour each other. Right now, the Milky Way is being circled by smaller galaxies, satellites like the Large and Small Magellanic Clouds, dwarf galaxies like Sagittarius and Canis Major. And over billions of years, we're going to consume them. This is galactic cannibalism, and it's happening everywhere. When galaxies collide, it's not like a car crash. Stars are so far apart that most pass by each other without touching, but the gravitational chaos is immense. Spiral arms are torn apart. Stars are flung into intergalactic space, becoming orphaned wanderers with no home. Gas clouds collide, igniting waves of star formation. And at the centers, supermassive black holes spiral toward each other in a death dance that can last millions of years. Eventually, the black holes merge, releasing a burst of gravitational waves so powerful it ripples through space-time itself, detectable across billions of light years. But if the most disturbing part isn't the collision, it's what comes after. When galaxies merge, they don't become two separate objects sharing space. They become one, a new galaxy shaped by violence, its structure warped by the collision. The Milky Way is heading toward its own galactic merger. In about 4.5 billion years, the Andromeda galaxy will collide with us. From Earth, Andromeda will grow larger in the sky night by night, until it dominates the heavens. Then it'll fill the sky completely, a swirling chaos of stars and gas stretching from horizon to horizon. The collision will take millions of years, a slow-motion catastrophe, as two galaxies interpenetrate and merge. Stars from both galaxies will be scattered into new orbits. Some will be ejected entirely, flung into intergalactic space at escape velocity. Our sun might survive, or it might be hurled into the outer regions of the new galaxy, far from the galactic center where most stars cluster. Earth, if it still exists, will have a very different view of the night sky. But galactic cannibalism isn't limited to mergers between equals. Milky Way types have appetites for smaller galaxies, and they feed on them constantly. Most of it is asymmetrical. Large galaxies consume smaller ones, tearing them apart through tidal forces and absorbing their stars, gas, and dark matter. The Milky Way has consumed dozens of smaller galaxies over its lifetime. We can still see the remnants, streams of stars stretched across the sky, orphaned clusters orbiting at odd angles, ghostly traces of galaxies that no longer exist. And it's still happening. The Sagittarius dwarf galaxy is currently being pulled apart by the Milky Way's gravity. Its stars are being stripped away, forming long streams that wrap around our galaxy like ribbons. In a few billion years, it'll be gone completely, absorbed into the Milky Way's structure. But here's the unsettling part. We're inside a cannibal galaxy. Every star you see, including the Sun, is part of a system that's actively consuming smaller galaxies. We're not observers, we're participants. Our galaxy is a predator, and we're along for the ride. And this isn't rare. Galactic cannibalism is one of the primary ways galaxies grow. Large galaxies in the modern universe are the survivors, the ones that consumed enough smaller galaxies to become giants. The universe we see today is the result of billions of years of cosmic violence. Galaxies eating galaxies eating galaxies. It's natural selection on a galactic scale. But galactic cannibalism has another consequence. It disrupts star formation. When galaxies collide, gas clouds are compressed, triggering bursts of star formation. But the same collisions can also heat gas to the point where it can't collapse into new stars. Over time, merged galaxies often become red and dead, elliptical galaxies with old stars and little ongoing star formation. This might be our future. After the Milky Way and Andromeda merge, the resulting galaxy, nicknamed Milkomeda, will likely be an elliptical galaxy dominated by aging stars. No more spiral arms, no more beautiful disk structure, just a blob of stars orbiting chaotically around a central supermassive black hole. And if Earth survives, its night sky will be dimmer. Fewer young, bright stars, more red giants and white dwarfs. The sky slowly fading as the galaxy ages and its stars die, one by one. Galactic cannibalism is a reminder that nothing in the universe is permanent. Not galaxies, not star systems, not even the night sky itself. Everything is in motion. Everything is colliding. Everything is being consumed or doing the consuming. And we're just passengers in a galaxy that's been eating its neighbors for billions of years.
We think of empty space as stable, inert, safe. We might be wrong. There's a theory in physics that the vacuum of space, the very fabric of reality itself, might not be in its lowest energy state. Instead, it could be in a false vacuum, a metastable state that's temporarily stable but not truly permanent. And if that's true, the universe could end at any moment. Here's how vacuum decay works. Quantum fields permeate all of space, including the vacuum. These fields have energy levels, and normally they settle into their lowest possible energy state, the true vacuum. But what if our universe's vacuum isn't at the lowest level? What if it's stuck in a higher energy state, like a ball balanced on a hill instead of resting in a valley? Eventually, that ball will roll down, and when it does, reality itself will change. A vacuum decay event would begin at a single point, somewhere in the universe, possibly triggered by a quantum fluctuation or high-energy particle interaction. At that point, space would transition to its true vacuum state. This transition would create a bubble, and inside the bubble, the laws of physics would be different. Atoms might not form the same way. Particles could have different masses. Fundamental forces might change strength. Everything that depends on the current vacuum state, chemistry, biology, stars, planets, life, would cease to function. And the bubble would expand at the speed of light. There would be no warning, no way to see it coming. Because the leading edge of the bubble moves at light speed, no signal could outrun it. The first indication that vacuum decay had begun would be the moment it hit you. And then you'd cease to exist. Not just you, everything. Stars would disintegrate. Atoms would fall apart. Reality itself would unravel.
the bubble would expand forever, consuming galaxies, galaxy clusters, eventually the entire observable universe. Nothing could stop it, nothing could survive it. And the worst part? It might have already started. Somewhere in the distant universe, a vacuum decay bubble could be expanding right now, racing toward us at light speed. In 1 billion years, it'll reach the Milky Way. In 1 trillion years, it'll consume everything we can see. But we'd never know until the moment it arrived. That's the terror of vacuum decay. It's not a question of if, it's a question of when, and whether it's already begun. Some physicists calculate our vacuum is stable. Others say it's metastable, balanced on the edge. A few suggest we're in the true vacuum already, safe from this particular apocalypse. But nobody knows for sure. Because to test it, you'd need to probe the vacuum at energies we can't achieve. And even if we could, we might accidentally trigger the very thing we're trying to prevent. High-energy particle collisions, like those at the Large Hadron Collider, could, in theory, nudge the vacuum toward decay. It's incredibly unlikely, but not impossible. And that's led to some uncomfortable questions. Should we be doing these experiments? Are we risking the entire universe just to learn more about physics? Most scientists say no. The risk is negligible. But negligible isn't zero. Vacuum decay is the ultimate Russian roulette. Every high-energy event, every particle collision at the edge of physics is pulling the trigger. And we don't know if the chamber is loaded. If the vacuum decays, there's no escape, no preparation, no survival. Just an instantaneous transition from existence to non-existence. And perhaps, in the vastness of the multiverse, it's already happened countless times. Other universes, other realities, snuffed out by vacuum decay, their laws of physics rewritten in an instant.
We might be living in a temporary universe, one of many bubbles in a cosmic foam, each one destined to eventually decay and give way to something new. Or we might be lucky. Perhaps our vacuum is stable after all. Perhaps the universe we see is the way it's supposed to be, and we have nothing to fear. But we won't know until it's too late. That's the nature of vacuum decay. It's the ultimate existential threat, invisible, inevitable, and absolutely final. And somewhere in the universe, the clock might already be ticking. When the universe was born, it didn't emerge smoothly. As it cooled from the Big Bang, phase transitions occurred, like water freezing into ice. And these transitions might have left defects in the fabric of space-time. Cosmic strings. Think of them as cracks in reality. One-dimensional objects, infinitely thin but incredibly dense, stretching across light years or more. And if they exist, they're among the most dangerous objects in the universe. A cosmic string would have no thickness, zero width, but it would have mass, enormous mass. A single meter of cosmic string could weigh as much as Mount Everest. Now imagine one millions of light years long. These strings wouldn't sit still. They'd vibrate, writhing through space like cosmic whips. And when they move fast. Segments of cosmic string could oscillate at near light speeds, releasing gravitational waves and tremendous energy. If a cosmic string passed through our solar system, the gravitational effects would be catastrophic. Planets could be pulled from their orbits, asteroids would rain down on Earth, the sun itself might wobble, destabilizing the entire system. And if a cosmic string passed through Earth directly, it would slice the planet in half. Not metaphorically, literally.
The string's gravitational field would be so intense and localized that anything crossing it would be torn apart by tidal forces. The two halves of Earth would separate, trailing debris, atmosphere venting into space. And it would happen in an instant. No warning, no defense. Just a line of destruction cutting through the planet faster than sound, faster than light in some cases, leaving nothing but ruin in its wake. But it gets worse. Cosmic strings can form loops. When a string intersects itself, it can break off, creating a closed loop that oscillates and gradually radiates out its energy as gravitational waves. These loops could be anywhere. Drifting through interstellar space, passing through galaxies. Some might be small, meters across. Others could span light years, and we'd have no way to see them until they were right on top of us. Cosmic strings don't emit light. They don't interact with normal matter except through gravity. They're invisible, intangible, and potentially lethal. Astronomers have searched for evidence of cosmic strings by looking for their gravitational effects. If a string passed between us and a distant star, it would create a distinctive lensing effect, bending light in ways that differ from normal gravitational lensing. So far, we haven't found any. But that doesn't mean they don't exist. It just means we haven't looked hard enough, or we've been lucky. Some theories suggest cosmic strings are rare, confined to regions of the universe far from any galaxies. Others propose they're more common, but generally too small to be detectable.
And there's another possibility. Cosmic strings might have already passed through our solar system millions of years ago, leaving no trace except gravitational ripples that have long since faded. But here's the truly unsettling part. If cosmic strings exist, and if one happens to be moving through the Milky Way, it could cause havoc on a galactic scale. A cosmic string passing through a star would disrupt it, possibly triggering a supernova. A string passing through a molecular cloud could fragment it, preventing new stars from forming. A string moving through a galaxy cluster could scatter galaxies, reshaping the large-scale structure of the universe. And we'd never see it coming. Cosmic strings are the ultimate invisible threat. Silent, invisible, unstoppable. They're scars left over from the universe's violent birth, still echoing through space-time billions of years later. And if they're out there, we're living in a universe with landmines scattered through space. Defects in reality itself that could annihilate anything they touch. The good news is that cosmic strings, if they exist, are probably rare and far away. The bad news is probably isn't certainty. And in a universe as vast as ours, even rare events are inevitable given enough time. Somewhere, a cosmic string might be oscillating through the darkness, its gravitational waves rippling outward, unseen and undetected. And if its path crosses ours, we'll have only one moment to realize what's happening before everything ends. Every process in the universe generates entropy. Heat disperses, energy spreads out, order decays into chaos. And eventually, the universe will run out of usable energy entirely. This is the heat death of the universe, and it's the most likely ending for everything that exists. Here's how it happens. The universe is expanding. Galaxies are moving apart, carried by the acceleration of space itself. As they recede, the distance between them grows, and eventually they'll be so far apart that light from one galaxy will never reach another. Each galaxy will become isolated, alone in its own pocket of space, surrounded by darkness. Inside those galaxies, stars will continue to burn for trillions of years, but eventually they'll run out of fuel. One by one, they'll die, fading into white dwarfs, neutron stars, or black holes. Star formation will slow and then stop entirely as gas clouds are used up. The last stars will flicker out,
leaving galaxies dark and cold. Planets will drift, frozen and lifeless, orbiting dead stars. Black holes will continue to grow, consuming anything that wanders too close. But even they won't last forever. Through a process called Hawking radiation, black holes slowly evaporate. The larger the black hole, the longer it takes. But eventually, every black hole in the universe will radiate away its mass and dissipate. The supermassive black holes at the centers of galaxies, billions of solar masses, could take 10 to the 100 years to evaporate. That's a 1 followed by 100 zeros. A time span so long, it's almost meaningless. But even that will end. After the black holes are gone, the universe will be a sea of elementary particles, photons, neutrinos, maybe a few electrons, spread so thin that interactions become vanishingly rare. Temperature will approach absolute zero, entropy will be maximized, and nothing will ever change again. This is heat death. Not a dramatic explosion, not a cataclysm, just fading. The universe will become a dark, cold, empty expanse where nothing happens, because there's no energy left to make anything happen. No stars, no planets, no life, no thought, no movement. Just particles drifting in eternal silence, separated by distances so vast that they'll never interact with anything else ever again. It's the loneliest end imaginable.
But there's a strange comfort in knowing that heat death is trillions of years away. Humanity, if it survives, will have unimaginable amounts of time to explore, evolve, and perhaps find ways to delay or escape the inevitable. Some physicists have speculated about escaping heat death by creating artificial universes or exploiting quantum mechanics to extract energy from the vacuum. Others suggest that advanced civilizations could harvest the rotational energy of black holes, sustaining themselves for eons. But eventually, the universe wins. Entropy always increases. Energy always disperses. And in the end, everything fades to black. Unless, of course, we're wrong about how the universe works. There are other possibilities. The Big Rip, where dark energy grows stronger over time, eventually tearing apart galaxies, stars, planets, atoms, and even space-time itself. The Big Crunch, where the universe's expansion reverses and everything collapses back into a singularity. Vacuum decay, where the fabric of reality itself becomes unstable and rewrites the laws of physics. Each ending is different. Each one is final. But heat death remains the most likely scenario based on our current understanding of cosmology. And it's oddly poetic. The universe began in a burst of unimaginable energy, the Big Bang, and it will end in silence, in darkness, in stillness. From light to shadow, from chaos to perfect, eternal order. It's not the ending anyone wants, but it's the ending the universe seems to be heading toward. And when it arrives, there will be no one left to mourn, no observers to witness the final moments, just a cold, dark universe fading into oblivion forever. We've traveled through cosmic nightmares, storms that never end, planets that rain glass, stars that devour each other, black holes that warp time itself. But the most terrifying thing about the universe isn't what we've discovered. It's what we can never know. The observable universe is 93 billion light-years across, but the actual universe? It could be infinite.
It could be 1 trillion times larger, or it could loop back on itself in ways we can't comprehend. We'll never know, because light from beyond the observable horizon will never reach us. The expansion of space ensures that there are regions of the universe forever separated from us, not by distance, but by time itself. Galaxies beyond the edge are receding faster than light can travel, and as the universe continues to expand, more and more of it will slip beyond our reach. In the far future, 1 trillion years from now, any civilizations that arise will see a much emptier sky. Most galaxies will have receded beyond the cosmic horizon, leaving only a handful of nearby ones visible. They'll look up and think the universe is small, isolated, finite. They'll be wrong, but they'll have no way to know it. And the same is true for us. Right now, we're surrounded by an unknowable cosmos. Structures so vast we can't see them. Events so distant they'll never reach us. Perhaps entire universes pressed against ours, influencing us through gravity, but forever invisible. We're living inside a bubble, and we can never see beyond its edge. That's the ultimate cosmic horror.
Not monsters in the dark, not catastrophic disasters, but the realization that reality is bigger than we can ever perceive, and most of it is hidden from us forever. We'll never know what's causing dark flow. We'll never visit rogue planets drifting through interstellar space. We'll never understand what dark matter truly is, or why the universe is structured the way it is. We're limited by the speed of light, by the expansion of space, by the fundamental constraints of physics. And no amount of technology, no amount of curiosity will ever overcome those limits. But here's the beautiful part. Even within our bubble, there's more to discover than we could ever explore in 1,000,000 lifetimes. Billions of galaxies, trillions of stars, worlds beyond counting, each one unique, each one telling a story about how the universe works. We've only just begun. Every answer reveals new questions. Every discovery opens new mysteries. And the universe keeps surprising us, keeps showing us that it's stranger, more complex, and more wondrous than we ever imagined. So yes, the universe is terrifying. It's violent. It's hostile. It's filled with things that can destroy us without even noticing we exist. But it's also beautiful. And it's ours to explore. For as long as we exist, we'll keep looking up. We'll keep asking questions. We'll keep pushing the boundaries of what we know. Because that's what humans do. We explore. We discover. We refuse to accept that something is unknowable just because it's difficult. The universe may be terrifying, but we're not backing down. We're here. We're curious, and we're not stopping. So the next time you look up at the night sky, remember, every point of light is a sun. Every shadow could be a galaxy. And beyond everything you can see lies an infinite cosmos filled with wonders and horrors we've only begun to imagine. The universe is vast, it's ancient, it's terrifying, and it's waiting for us. We started this journey with a storm on Jupiter that's been raging for centuries, a storm that shouldn't exist, but does. And now, after exploring planets that rain glass, stars that cannibalize each other, galaxies that devour their neighbors, and the eventual fate of reality itself, we return to a simple truth. The universe doesn't care about us. It's not cruel. It's not kind. It simply exists, following laws we're only beginning to understand. And that makes it terrifying, not because it's actively hostile, but because it's indifferent. A gamma-ray burst could sterilize Earth tomorrow, and the universe wouldn't notice. A rogue black hole could wander through our solar system, and it would be just another gravitational interaction among trillions. We're insignificant on a cosmic scale, but we're not powerless. We can observe, we can measure, we can understand. And in understanding, we gain something the universe will never have: meaning. We look at a supernova and see both beauty and terror. We study black holes and feel awe. We map the cosmic web and recognize patterns. The universe may be indifferent, but we're not. We care. We wonder. We dream. And as long as we exist, we'll keep staring into the abyss, not because we're fearless, but because we refuse to look away. Because the most terrifying places in the universe are also the most fascinating. And we're determined to understand them, no matter what.